for me.
Violin almost sounds like violence.
Violence class.
I'll take a picture of
Violence
this.
class.
All right, so speed run review. We've never ever reviewed anything in this class. This is the first ever review.
Me,
Is it called inaugural review? Okay.
review everything.
The very first review.
So it's like combinatorial non-stanzas, yeah?
This might be faster as well.
Oh,
So-
oh my.
Alright.
Just give
Oh
up.
my god.
First thing is a lemma, yeah?
Lemma.
And then there's two theorems, yeah?
Theorem 1, theorem 2. We shall prove the lemma.
And then a ton of examples, yeah? Okay.
Lemma.
The lemma. It's actually the lemma that you've actually always wanted in your life when you deal with multivariable polynomials, but you're always worried that you're not getting the right one.
Yes.
Okay, so the lemma is basically saying if you have a multivariable polynomial,
Yes.
okay, and it has a degree in each of the variables, yeah,
Yes.
of f, yeah,
Yes.
then, and you have a bunch of sets, okay, of bigger size than the degrees, yeah, and f is 0 on all of those things, okay.
Back in the day, we'd go to 9 o'clock and still be bright outside, kind of.
We used to we used to end at 9,
Yeah.
and we never took breaks. I was just so naive.
Before.
Maybe it was better. I don't know.
I mean,
Maybe I was just able to last longer or something. I don't
Oh no, we have 3 minutes left with this lemma.
know.
The write-up is slower than.
Yeah. Okay. So you see, the lemma says if you have a bunch of sets that are bigger than the degrees, and f is 0 on tuples formed from those set elements,
Yes.
then it's 0. Okay.
Very blunt.
Yeah. So for example, like if you weren't too careful, like even my advisor, who was meant to be like the banner mathematician of Australia or something, would make a mistake, and he was very upset about it. He once made the statement that like if a polynomial in 2 variables has infinitely many roots, then it's the 0 polynomial.
oh,
Yeah. That's not true, right? Like x minus y, x times y, like all these things, infinitely many zeros aren't 0. But this is the one you're looking for. It only has finitely many zeros, but they're kind of in the right directions, yeah? So for n equals 1, it's just the normal thing you know, right? So for n equals 1, it's just, you know that a polynomial of degree n can only have the most n roots.
Wait, so if it's
Ooh.
so it's like the equivalent of the thing for one variable.
Yeah.
And then but then it's like saying if it has that many zeros in like kind of every element,
Yeah.
then
At this, like you have to sub them in at the same time. You can't just like sub in one and keep the other variables random. It's all from S, yeah? Yeah. So it's basically by induction, because if you assume it's true, right? Because you know n equals 1 is true. You can write any polynomial as sort of like these polynomials in n minus 1 variables as coefficients, and then the last variable it's like a polynomial of that variable. So when you sub in the first n minus 1 s's, right, then it turns into a polynomial in 1 variable, right? And so then when you sub in the last s, it's equal to 0. But there's too many s's, so the whole polynomial is 0. So then the coefficients here are all 0. And by an assumption, yeah. Okay. You can actually prove it as an exercise if you want. You just have to know a base case and it's induction, yeah? Okay, theorem 1. Theorem 1 of non-stanzas, yeah?
We're ahead of time. This is good.
Yeah. So if you define GI to be these polynomials where S is in SI of XI minus S, yeah? Okay. So GI are polynomials exactly when you sub in something from SI in the ith variable, and anything else, it'll be 0, yeah? And F is 0 Is this literally the only assumptions?
I think so.
S of S, f of S1 is 0 for all S.
Yes. That gets that.
Okay.
And this
So
is
another
the
way of saying this is the common zeros of G are all zeros of F. Okay, because the common zeros of G, well, so what's the zero? You know what I'm talking about? What's the zeros of G? They're anything of the form like something from SI in the ith spot, right? And anything else in the other spots. Because it only cares about that spot, right?
So
Yeah.
like none of the factors have to.
Yeah. So yeah, because G is already factorized, right? And so the common zeros of all the G's are the ones where it's like S1, S2, S3, S4, Sn. All right, because then all of them will be 0 at the same time. And so F is 0 on all the common zeros of G, right? And the conclusion is F equals the sum of HI GIs. Okay. Where HI are just n variable polynomials and GIs are these things. Okay. And what's moreover, if F and G all have coefficients in some subring of the field, the H's also have those coefficients. Okay, so if they're integer polynomials, H is an integer polynomial as well. Okay.
Transformation.
Yeah, we have 3 more minutes to prove this. So basically, what you need to do is if you can, so you don't need to conclude that F is 0, right? In the end, you need to conclude the sum of things, yeah? So you're allowed to do some stuff to F before you conclude it's 0, if you're going to use the first level, right? So what are you allowed to do to F? Well, hopefully you can do something to F to make its degree small enough so you can apply the lemma. Okay. At the moment, you don't even know what the degree of F is. Yeah. Okay. So basically, the proof is, because you only really care about, so G is monic, right? G is monic. So it's got the leading term is like, you can call it like you can suppose the degree of the leading term, you can define it to be like Ti plus 1. Yeah. And what that gives you is like gives you a basically a relation. So whenever G is equal to 0, you have x to the power of Ti plus 1 equals a whole bunch of lower power terms. Yeah. So Gi equals xi to the Ti plus 1 minus some lower order terms. Yeah. Okay, so, but when you sub in something that makes G 0, then x to the Ti plus 1 equals the lower order terms. Yeah. So after the substitution, you can use this relation to decrease the power of the xi's. Yeah. Okay. So what that corresponds to on the polynomial level is, so you're substituting that for that, right? So on the polynomial level, what you're doing is you're essentially subtracting a multiple of Gi from F. Yeah. Does that make sense? So if F was like, if Gi was equal to like x squared minus something, right? Right? Minus like x, yeah. And F was like x cubed, right? So you want to replace it. You want to replace x squared by x, yeah? So then this becomes x times x, yeah? Where you replace the x times x squared by x times x, right? But that's the same as, you know, so x cubed minus x times x squared minus x, yeah? So you're just subtracting a multiple of gi, yeah? Okay. Oh, time's up. Okay.
Your time is up. Please proceed.
Okay.
to
So the
next
point is, once you've subtracted all the multiples of gi, all the degrees are right now, and so you can apply the lemma. Okay. And so it's 0. So then f minus a bunch of sums of HIGI is equal to 0. So f is equal to sum of HIGI.
And why can't you apply the number? So you get all the degrees down to 1.
Yeah.
Wait,
Actually,
if
there's
it-
another
wait,
thing I didn't say here. The conclusion also has the degree of HI is at most the degree of f minus the degree of GI.
Red is sus.
Okay.
Wait, hang on.
Among
Yes.
Us.
Okay.
Wait, after you reduce the degree,
Yeah.
and then what?
Once you reduce the degree, you apply the lemma to the reduced degree thing.
Wait, why are you?
Because the lemma only said that the degrees are smaller than the set
Oh yeah,
sizes,
so
right?
it's bigger than you have to
Why
make the
are the
degrees
legs
smaller.
like that?
Yeah.
When he's facing the other way.
So you define the set sizes to be the yeah.
That's even more better. Donkey.
Okay, so we're good. All right, last theorem. We have 3. Well, how come we just lost 2 minutes? All right, anyway, so
Oh, we're down on time.
Oh no, speed run, speed run, speed run, please.
okay, so this is the one that you came in. We know the statement, right? So it's basically degree of f is equal to a bunch of sum. It's like it can be partitioned to the sum of ti's, and it can be realized by this monomial. Yeah.
Code red, speed run.
Okay. And then we have the sets of sizes bigger than these ti's. Yeah.
Yeah.
Then the conclusion
Even do TP test,
is
yeah.
that f is not 0. Is not 0 for some s in these things, yeah. Okay. Is that the correct statement?
Yes.
Okay, so then the proof is basically 2 minutes. So you assume for contradiction it is 0, right? If it is 0, then you get the first theorem gives you that it's equal to a sum of HIGIs, right? Okay, but because it has an XITI term, right? The HIGIs have to have an XITI term, okay? Right? So some HIGI has to have this XITI term, right? Okay, but look at the HIGIs. The HI degree plus the G degree is at most F, right? So to reach it, you have to get the biggest thing from G and the biggest thing from H, right? Well, the problem is, look at G, right? The biggest thing from G has SI as its degree, right? Yeah, and SI is bigger than TI, right? So anything that comes out of that will have a power bigger than TI, so it can't ever give you the XITI. Yeah, that's a contradiction. So yeah, wow.
What a speed run.
Finish 1 minute.
Yeah.
Submit this on YouTube. The shortest proof of